Welcome back to a course on complex analysis. In the previous lecture, we have seen a theorem which is to be used in proving the maximum modulus principle. That is the agenda for today's lecture. So here in this lemma, we just proved if a function satisfies this condition, that is absolute of function smaller than or equals absolute of z naught, and the z naught is a center of like around z naught you take some neighborhood, and this property is holding in a neighborhood. Okay, so that in that neighborhood your function is analytic. Okay, if you talk about the analyticity in a neighborhood, it means what it at all the points of the neighborhood the function is analytic. So if that is so, if this condition is satisfied, then we can very well say that f of z, this function is a constant. Okay, if you know the value of f of z naught, that is going to be the value of the function throughout that neighborhood. This is what we proved in this lemma. With the help of this lemma, we are actually now ready to prove the maximum modulus principle. Okay, here what is given? It is given that a function f is analytic. Okay, so analyticity is there and is not constant in a given domain D, which means your f of z is f of z is not constant. Okay, there is nothing more to explain about it. If it is not constant, it means it takes different values for different z. Okay, f of not constant in the given domain D. So you don't know what is your domain. Suppose if this is your domain, inside this domain we are talking about things. Inside this domain you can take any point, and if you substitute that in the given function f, you are going to get different values for different z. Okay, if this is the case, then your absolute of f of z has no maximum in D. So when we talk about in D, we are talking about the interior of D. Okay, so there are some terminologies which we'll have to understand. In D means interior of D. Okay, on D means on the boundary of D. Okay, uh, if it is outside D means that is exterior of D, or we say it as outside D, that we know. Okay, so here it is said that in D, which means inside this. Okay, if you consider this as, okay, this is a domain, right? So inside this, on the interior points of this domain, we will not have any maximum value. That is what we'll have to prove. Okay, so that is rewritten in another way. There is no point z naught in the domain such that this is happening for all the points in the domain. So this is what we'll have to prove. Okay, how are we going to prove? We will make use of contrapositive approach to prove this one. So let us start the proof formally, right? So it is given that f is analytic in the domain D. Okay, so let us do a contrapositive approach. Since uh, the function can be proved to be constant if some certain conditions are satisfied. That is what we have proved in the previous lemma. We would like to incorporate that lemma to prove this theorem. So we will make use of contrapositive approach. Assume that absolute of f of z has a maximum value at some point z naught in D. Okay, then our claim is f is constant. Why should we prove this one? It is just because this analyticity is assumed in general. Okay. Now, if you assume if f of z is not constant, you will have to prove absolute of f of z has no minimum in D. You have assumed the contrapositive statement of the result. That is, we have assumed absolute of f of z has a maximum value at some point in D. So, you cannot neglect the analyticity that is required anyway. So, we can just prove this function is constant. Okay. How are we? This is constant throughout D. So, this is what we'll have to prove. Okay. Now, what are we going to do? So, take okay, let me just give you a, a diagram kind of a thing to understand things in a better way. So let this be our D. Okay, you can consider any region D, and let this be my Z naught. Okay, and we'll have to choose some other point P inside this domain. Okay, what we are going to do is that we connect these two points using polygonal lines. So hope you know what do we mean by polygonal lines. Okay, we just join these two points using polygonal lines. In between you can introduce few points as well. Okay, it goes till, let this point be Zn, and before which what you have is Zn minus 1, Zn minus 2. In this way we are constructing these things. Now you okay, so I hope now what I am trying to convey, right? So these are the things. Let us write them in wordings as well. So we draw, okay, let P be any point in D such that P is not equal to Z naught. So this is the point that we are taking, right? We now draw, a polygonal line L that is lying in D and extending from Z naught to P, which is same as that of our Zn, right? And let us take D be the shortest distance from the points on L to the boundary of D. In simpler terms, D is minimum of absolute of Z minus omega, where Z is taken in L and this W is taken on the boundary of D. Okay, so if you just understand the shortest distance without this notation itself, it is completely fine. We are not going to use these notations in the proof. Okay, just for the understanding purpose I have given you these things, right? When D is the entire plane, what? Okay, that is, if D is an entire, D is the entire plane. So when we talk about entire plane, it means what? See, then your small d may have any positive value, or sometimes it is infinity even. Okay, next we observe that there is a finite sequence of points z1, z2, actually starting from z0, z1, z2, etc. till zn minus 1, zn along the line L, such that zn coincides with p. Okay, and we have absolute of zk minus zk minus 1 is smaller than d for k running from 1 to n. Okay, now when we form these things, we can take neighborhood of the z naught. Okay, make sure that when you take a neighborhood of the z naught, the point z1 is covered inside this. Okay, sorry, and let us name it as n naught. Next, when you take neighborhood of the z1, make sure that it is covering the point z2, and when you make a neighborhood of this one, you are covering the point z3. So in this way you will have to take neighborhoods. Okay, so hope you get the ideology. The diagram may not be clear to you, but still the ideology is clear to you, I hope. Okay, so in forming a finite set of in forming a finite sequence of neighborhoods, that is n0, n1, n2, etc. till nn minus 1 nn, where each nk has center ck and radius d. Okay, what is d? That is the shortest distance between the points on the line to the boundary of this one. So you will have to choose the d as the radius of the neighborhood, and you have to form this one. So when you do so, of course your points are covered in this fashion. Okay, so okay, fine. Radius is d. Mm, since okay, let us move further. uh, Here your f is analytic. It is given to be analytic in entire d. So here f is analytic in each of these neighborhoods. Since all of these are contained in d, that is why it is happening to be true. And the center of each neighborhood nk with k starting from 1 to n lies in the neighborhood nk minus 1. That is very obvious, right? So if you take the point z1, that is lying in the neighborhood of z0. If you take the point z2, that is lying in the neighborhood of z1. Okay, why is it happening? Just because uh, we have chosen d to be the minimum distance between the points on the line and the boundary, and by our observation we very well noticed that this happens. Okay, so that is why it is happening. So with which, what can we say further? Okay, by our assumption, absolute of f of z has a maximum value at z naught. This is for all z and d. So if this is so, then your absolute of f of z has a maximum value at z naught in the neighborhood n naught. By the previous lemma, we can very well say that your f of z equals f of z naught for z in the neighborhood n naught. Since z1 is a member of n naught, we have f of z equals f of z naught equals f of z1. Okay, therefore in n1 f of z has a maximum value. Your absolute of f of z has a maximum value at f of z1, right? So it means what? Hence you will have f of z is same as that of f of z naught is same as that of f of z1, which is same as that of f of z2. Okay, repeated application of this idea, we get f of z equals f of z naught for all z in n naught, n1, n2 till nn. Okay, so this d may be anything, like we can choose the entire complex plane also to be the domain d. This is what we have already said. Using those ideology, we can actually conclude this one, right? So with which, like, what to say? So therefore, f of z is f of z naught for every point z in d. Hence, f of z is constant. So with which, what can we say? If f of z is analytic and non-constant, such that f of z has no maximum in d, like, sorry, non-constant in D, then f of s has no maximum in D. So this is what we have just proved. Okay, this is that. Next, we further continue our discussion. If f of z is analytic at each point in the interior of a closed bounded region R, then f of z is continuous in the continuous throughout R. So this tells us that absolute of f of z has a maximum value somewhere in R. Now what we are about to derive is that this absolute has a maximum value on the boundary of R, not in the interior of R. This is what we are trying to prove. Okay, if this has a maximum value somewhere in R, it means what? It means that is there exists a M positive such that, okay, not positive and non-negative quantity such that absolute of f of z is smaller than or equals M for all points z in the region R. Okay, and the equality happens in at least one point. Okay, this equality occurs at least in one point. So the next thing that we are going to discuss is important special category. If f is constant function, then absolute of f of z equals m for all z in R. Okay, so whether we have a like a so if it is constant, okay, fine. So this is happening, right? So with the ideologies that we have just discussed, we have the important corollary. So what is that? If a function is continuous on a closed bounded region R, that is analytic and is not constant in the interior of R. Okay, that is not constant in the interior of R. If it is constant in the interior of R, then what happens? Every value are same. If it is not constant, then we are going to have this one, like the one which is written here. Okay, this is going to happen. The equality will happen at least in one point. But what? Your absolute of f of z is not equal to m for points in interior. Okay, so then of course the maximum value must occur in the boundary of the region, right? So here we are going to see a small example. Here your R denotes the rectangular region, that is 0 smaller than x smaller than or equals phi, sorry, pi, and 0 smaller than or equals y smaller than or equals 1, and the function is given to be sin c. You can just verify the principle that we have seen here in the form of corollary. What you have is mostly referred as maximum modulus principle by several authors. Okay, if you have a continuous analytic function that is defined on a closed region, then the maximum of that function occurs only on the boundary, not in the interior. That is the ideology, main ideology that you have to remember about maximum modulus principle, right? So you have this one, and when you try to segregate real and imaginary parts, you can very well see it is sin x cos iota times of y plus I times of, actually what you want to get is cosine x plus sin iota times of y. So this gives you sin x hyperbolic cos y plus cosine x. This is I times of hyperbolic sin y. So with which if you write what is your f of c squared, this is sin squared x cos s squared y plus iota times of, sorry, you will not have iota, cos square x plus hyperbolic sin squared y. So it is sin squared x. Let us replace this one as what, or if you can have this as it is, have it, and this cos square may be written as 1 minus sin squared x sin h squared y. So if you just combine things up, you would get cos h squared y minus sin h squared y plus sin h squared y. So cos h square y minus sin h square y is 1. So what we get is sin squared x plus sin h squared y. So from this, if you write your absolute of f of c, that is under root sin squared x plus sin s squared y, right? So your sin reaches maximum when x equals pi upon 2. Okay, so that is a part of the given rectangle. Good. The next one is 0 less than or equals y less than or equals 1, for which your sin h square y reaches maximum when x equals 1. So with which if you have to complete at the point pi by 2 comma 1, this function reaches its maximum, right? So we have proved the results for the maximum value, and here the important point that I would like to record is these results are true even for smaller values as well, that is for the minimum values as well. That I leave it as an exercise to you people. Thank you.